For this recording, we are going to talk about the process of pulmonary ventilation. So let's set up the conditions at rest. So normal atmospheric pressure, we call it standard pressure, is 760 millimeters of mercury. And in the lungs, if there was no air movement, the pressure inside the lungs, or intrapulmonary pressure, would be 760 millimeters of mercury. So we call this the resting position, which means that you're not inhaling, you're not exhaling, there's no air moving. Okay? And the reason that there's no air moving is because there's no gradient. So the pressure of air in the atmosphere is equal to the pressure of the air in the alveoli, and therefore there's going to be no air movement. We're basically at equilibrium. Remember that your lungs are suspended in your cavity by the two pleura. Okay? The visceral pleura is attached to the lungs, that's the inner membrane, and the parietal pleura is attached to your thoracic cavity. And in between we've got the pleural cavity, which has pleural fluid and also contains a suction that causes the lungs to essentially be attached to the thoracic cavity. They're not physically attached, but the suction is keeping the lungs inflated and attached to the thoracic cavity. We have the diaphragm muscle, which is the primary breathing muscle, and in the resting position, the diaphragm muscle is in the up position. Okay? And we've also got an intrapleural pressure, which we won't talk about at this point. I think we're going to start on a more basic basis, and then we'll talk about that. Or you can learn about that later on in future classes. Alright, so we are at equilibrium. We're at rest. Okay? And you're at rest for two different senses. Basically, you're at rest, meaning you're not exercising, and you're at rest, your breathing is at rest, which means that you're not inhaling or exhaling. So when breathing is at equilibrium, breathing is at rest, the intrapulmonary and atmospheric pressures are equal, there's no air movement. Okay. So remember that we need to create a gradient if we want to move air. And if we want to inspire, we want air to move in. Okay. And we want air to move from the atmosphere into the lungs. Okay? So where do we want pressure to be higher? Okay, we want pressure to be higher in the atmosphere than in the lungs. Okay, in order to go from high to low pressure, we want air to come in, we want the atmospheric pressure to be greater. And the way we cause this to happen is not by changing the atmospheric pressure, because we don't have the ability to change the atmospheric pressure, but what we can do is we can change the lung pressure. Okay? So if they're currently equal and we want the atmospheric pressure to be greater, then what we can do is reduce the pressure in the lungs. Okay? And remember what Boyle said. Remember what Boyle said is that if we increase volume, we will decrease the pressure. Okay, so if we increase the volume that's holding the gas, we will decrease the pressure of the gas. Okay, so if we want to decrease the pressure in the lungs or in the alveoli, what we can do is increase the volume of the alveoli. Okay? And that's exactly what we do. Okay? So, where are we? Okay, so what happens is that your inspiratory muscles contract. Your inspiratory muscles are your diaphragm and your external intercostals. Okay? When the diaphragm contracts, it drops. Okay? When the external intercostals contract, they lift the ribs and the sternum. Okay? So when the diaphragm drops, the thoracic floor drops, and the ribs and sternum lift when the external intercostals contract. So basically what's happening is the thoracic cavity is getting bigger. Okay, so if you look here, we've got the diaphragm in the up position. If we drop the diaphragm like this, the thoracic cavity is going to expand down. Okay, the lungs are not actually connected to the diaphragm physically, but the parietal pleura is attached to the thoracic cavity and the diaphragm. So if the diaphragm drops, then the parietal pleura is going to expand down, and because of the suction in the pleural cavity, the lungs are going to expand. Okay? And you can see here that the volume of the lungs is getting bigger. Okay? The other thing that happens is that when your external intercostals contract, your rib cage lifts. Okay? When your rib cage lifts, your lungs expand front to back, which I can't show you on a two-dimensional screen. So basically, when the diaphragm contracts, the lungs expand down, so they get taller. When the external intercostals contract, the lungs are lifted away from the chest, because as the ribs lift, the lungs lift, and it's like you're taking a balloon and you're pulling it open. Okay? So the diaphragm and the external intercostals, when they contract, it causes the thoracic cavity volume to increase. Okay? Whatever happens to the walls of the thoracic cavity are also going to happen to the lungs because of that suction. So the lung volume is going to get bigger. And according to Boyle, if you increase lung volume, you're going to decrease lung pressure. Okay, so we started with the pressures being equal. If we decrease intrapulmonary pressure, then what we have is atmospheric pressure being greater. Okay? So the lung pressure was P2, and if we drop P2, we're going to have a bigger gradient between P1, or we're going to have a gradient because we didn't have a gradient. And so P1 is going to be bigger than P2. Air is going to flow from the atmosphere into the lungs. Okay? Now, is this movement active or passive? Okay? So we started at equilibrium. How did we generate the gradient? Was it natural, or did we have to do work? Okay, we had to do work. These muscles had to contract. Okay, so we had contraction. We used ATP. Therefore, in order to generate that pressure gradient, to drop the pressure inside the lungs, set up a gradient between the atmosphere and the lungs, we had to actively cause this gradient to occur. Now, as atmospheric pressure is greater than pulmonary pressure, the air is going to flow into the lungs from the atmosphere, and as air is flowing into the lungs, the pressure in the lungs is going to rise. So when enough air comes in, you're going to be back to where we started. We're going to be back to equilibrium. So as air flows into the lungs, pulmonary pressure rises, and so eventually the intrapulmonary pressure and the atmospheric pressures will then again be equal. Okay. So this is what it looks like. Inspiration. So you can see that the diaphragm dropped. You can't see, but when the external intercostals contracted, the rib cages lifted, so the lungs expanded from front to back. Okay, so the atmospheric pressure didn't drop, but the intrapulmonary pressure dropped. Remember, it was 760, now it's 758. Okay, because we got an increase in volume, which caused a decrease in pressure. So it went from 760 to 758. Now we have a gradient. Okay, atmospheric is greater than intrapulmonary. We have a gradient of 2 millimeters of mercury. This is going to pull air in. As air comes in, that pulmonary pressure is going to rise. And once that pulmonary pressure gets back to 760, we're back to equilibrium, and no more air is going to come into the lungs. Okay? So that's inspiration. Now, expiration is just the reverse. It's pretty easy to understand. So now, at the end of inspiration, we've taken in enough air so that we're back to equilibrium. We don't have a pressure gradient anymore. At this point, our inspiratory muscles, our diaphragm and our external intercostals, they simply relax. Okay. And when a muscle relaxes, it goes back to its normal, it shrinks back to its normal resting position, right, because of the elastic properties of muscles. So the diaphragm is going to go back up. The external intercostals are going to cause the ribs and sternum to go back down. Okay, this is going to cause the thoracic cavity volume to decrease. And because the lungs do whatever the thoracic cavity does, the lung volume is going to decrease. And according to Boyle, if lung volume decreases, intrapulmonary pressure increases. So now intrapulmonary pressure is greater than atmospheric pressure, which means air is now going to move from the lungs out into the atmosphere. Okay, that's expiration. That's how we exhale. Okay. Now, is this process active or passive? Okay. This is passive. Okay. This is a natural gradient that occurs when these muscles relax. So we didn't have to do any work when we relaxed the muscles. We only had to do work when we contracted the muscles. So when you're done contracting, relaxation is automatic. Okay. And therefore, the volume will decrease, the pressure will increase, and then what we're going to have here is a rise in pressure inside the lungs. So now what we have is the lungs is P1, the atmosphere is P2, because the lungs is a higher pressure. Air is going to move out. Okay? And as air moves out of the lungs, as air leaves the lungs, gases are leaving the lungs, the intrapulmonary pressure will start to drop. And eventually, the pressure in the lungs will drop to a point that the atmospheric pressures and the intrapulmonary pressures are again equal, and there's no more pressure gradient, which means air stops coming out. So you end up back at equilibrium again, and ready for another inspiration. Okay, so basically in expiration what we got was the diaphragm went up, shrinking the height of the lungs. The external intercostals relaxed, which means that the rib cage dropped, shrinking the size of the lungs from the front to the back of the chest. Okay, and So as we got a decrease in volume, the pressure inside the lungs increased. Okay, so remember it was 760, now it increases up to 763, setting up a gradient that favors air coming out. As air comes out, the pressure is going to drop inside the lungs from 763 to 762 to 761. Once it gets to 760, we're back at equilibrium. No more air comes out. Expiration is over. And now you've got a complete respiratory cycle. All right, let me talk briefly about what happens during exercise. Okay, so remember that inspiration is active at rest. We have to contract our inspiratory muscles in order to inspire. During exercise, inspiration is even more active. And this is because some additional muscles become involved. So at rest, we have the diaphragm, and we have the external intercostals, that contract. Okay, when you exercise, the sternocleidomastoid, the scalenes, and the pectorals also contract during inspiration. Okay, and what this does is causes an increase in the ventilation. Remember that ventilation is frequency times tidal volume. Okay, and if ventilation increases, it's either because frequency or tidal volume have increased. Okay, in terms of inspiration, the inspiratory muscles, these additional accessory muscles, allow you to inspire greater volumes of air, and with a greater tidal volume, you're going to have a greater ventilation. Okay. So let me just show you what that looks like. Okay. So if you add the accessory inspiratory muscles. Okay, so in addition to having the diaphragm contracting and the external intercostals contracting, you're also going to add sternocleidomastoid, scalenes, and pectorals. Okay, and so if you have more muscles contracting, what you're going to get is greater contraction strength. Okay, which means that you're going to get greater lifting of the ribs and sternum. Okay, because these three accessory muscles help the external intercostals. Okay, so we get greater lifting, a greater contraction strength means the ribs and the sternum are going to raise even higher. So think about it when you see someone exercising, you can really see their chest rising because these external muscles are causing a greater lifting. Okay, so if you have a greater lifting of the ribs and the sternum, you're going to have a greater expansion of the thoracic cavity, which means you're going to have a greater expansion of lung volume. Okay, so a greater lung volume, because remember the lungs, because of the suction, they're going to expand if the thoracic cavity expands. So if the thoracic cavity expands more, the lungs are going to expand more, so you're going to get a greater increase in lung volume. and therefore you're going to get a greater drop in intrapulmonary pressure. Okay, so more of an increase in lung volume is going to mean more of a decrease in pressure, okay, because of what Boyle says. Okay, so we're talking about inspiration, so we're talking about air moving into the lungs. So P1, P2, because it goes from high to low. So what happens is if we get a bigger drop in intrapulmonary pressure, that means P2 is dropping. Okay. That means P1 minus P2 is rising, bigger gradient. Okay, because P2 is dropping. And with the bigger gradient, that means there's going to be more air that needs to come in until that gradient is gone. Okay. So with the bigger gradient, and with exercise, we see a gradient of about 80 to 100 millimeters of mercury. Remember that the inspiratory gradient at rest was only about 2. So we get a much bigger gradient, which means you're going to get more air that needs to come into the lungs before equilibrium is reached. Okay. And more air into the lungs means greater tidal volume. Right? Because tidal volume is the volume of air coming into the lungs with each breath. Okay. And if you have more tidal volume times frequency is ventilation, you're going to have more ventilation. So more air is going to come into the lungs per minute, which means that you're going to have more oxygen coming in, and you're going to have more CO2 being removed. And this is going to help you during exercise, because that's a time when you need to bring more air in and at a faster rate, and because you need to bring in more oxygen and you need to get rid of more CO2. Okay? So that's inspiration during exercise. Expiration during exercise, remember that expiration at rest is passive. It occurs automatically because when the muscles relax, they shrink, which shrinks the thoracic cavity, shrinks the lungs, raises pressure inside the lungs, drives that air out. But what we find during exercise is that we get some accessory muscles that become involved in expiration. So the internal intercostals start to contract, the abdominal muscles start to contract. Okay? And when the internal intercostals contract, what they do is they pull the ribs and sternum down. So instead of waiting for the external intercostals to simply relax and recoil, the internal intercostals are going to pull the ribs and sternum down. And as it pulls the ribs and sternum down, you're going to shrink the thoracic cavity. Okay? And abdominal muscles are going to push the diaphragm up. Okay? And by pushing the diaphragm up, you're going to shrink the thoracic cavity faster. Okay? So what effect does this have on ventilation? You're going to get an increased rate of ribs, sternum dropping, and diaphragm raising, okay? Which means you're going to get an increased rate of the thoracic cavity volume decreasing, okay? Because when these two things occur, the thoracic volume gets smaller, and if these things happen faster, the volume is going to shrink faster. And remember that whatever the thoracic cavity does, the lungs do. So we're going to get a greater rate of the lung volume decreasing. Okay? And according to Boyle, if you change lung volume, you change pressure. So we're going to get a greater rate of intrapulmonary pressure increasing, okay? Because when Boyle says if volume decreases, pressure increases, and if volume decreases faster, pressure is going to increase faster. Okay? This is going to cause a faster rate of air flowing out of the lungs. Okay? Because this intrapulmonary pressure increase causes the gradient. Okay? So this causes an increased rate of generating the pressure gradient. And if we generate the pressure gradient faster, air is going to flow out faster. And if air can flow out faster, you can take your next inspiration sooner. Okay, so basically what this does is it increases breathing frequency. And remember, breathing frequency is a component of ventilation rate. So if breathing frequency is faster, then total ventilation is faster. We can bring in oxygen faster. We can get rid of CO2 faster. Okay? So the sooner you expire, the sooner you can take your next inhalation, which means that you can inhale and exhale more frequently in a minute's time. Okay? So instead of waiting for the air to exhale and leave and reach equilibrium before you take your next inspiration, we're basically forcing the air out. We're going to get it out quickly so we can take our next inhalation. This allows us to breathe more frequently, have more respiratory cycles within a minute, take more air in and out in a minute, and therefore bring in more oxygen, get rid of more CO2.